Hello calculus students, welcome to video 2C. This is Mr. Miller, and today we're going to talk about properties of limits. And we're going to talk about how to find limits of some very basic functions like polynomial functions and rational functions. Okay, here we go. First, some very basic functions. This is copied from the book. We're in section 2.2. I think this is 2.3 actually. Some basic limits. It says let b and c be real numbers and let n be a positive integer. I just want to explain what these mean. This first one is saying that the limit as x approaches some number c of a constant is equal to that constant. So what does that mean? So let me make an example. So if we had the limit as x approaches 2 of, say, 8. All right, well, I have a function that is always 8. For every value of x, it's 8. So as we get closer and closer to 2, the limit is just 8. So that's what this first one is saying. The limit as x approaches a number of a constant is just a constant. For instance, the limit of x approaches, say, 10 of -2. It's just going to be -2. This is a function that's -2 everywhere. So no matter what you approach, it's going to be equal to -2. All right, so that kind of makes sense. Let's try to make sense of this one. The limit as x approaches a number c of x is equal to that number. So here we go. Let's take the limit of x approaches, say, 5 of x. Well, this kind of makes sense. As x gets closer and closer to 5, the value of the function is equal to x, so the value of the function is going to get closer and closer to 5 also. So it kind of seems silly. The limit x approaches 5 of x is 5. Okay, so in this case, the function's equal to the input. So if the input's approaching 5, the function's approaching 5. Here's another example. Say the limit as x approaches -3 of x would, of course, just be -3. Okay, this last one is the limit of a power. So an example would be the limit as x approaches 4 of, say, x squared. What this says is just that is the number squared. 4 squared, which is 16. Okay, so it kind of makes sense. As x is getting closer and closer to 4, its square is getting closer and closer to 16. And here's another example. Suppose we have the limit as x approaches 2 of x cubed would just be 2 to the 3rd power, which is 8. Okay, so here are 3 real basic functions, a constant, x, and x to a power that we already know how to take the limit of. Now, there's some properties that I know at first seem really strange, or just a lot of notation. So we have 2 functions, and we're considering the limit as x approaches some number c here. So we assume that the limit of f is L and the limit of g is k. What this is saying is if we have some constant like 2 times the function, the limit is just 2 times whatever the limit was. And if we have a limit of a sum of 2 functions, the limit is just the sum of their limits. Alright, so I'll show you what these mean here in this example. So I'll talk about these properties as we break this down. So we have the limit as x approaches -3 of this polynomial function. That's what we're learning about, polynomial functions. So I can break it up. Limit x approaches -3 of 3x plus the limit as x approaches -3 of 2. Why can I break it up? That's this property right here, that if we're taking the limit of a sum of functions, like 3x plus 2, we can just add up their limits. That's what I did. I'm adding up the limit of 3x and the limit of 2. Now, I can take this constant out front. Why can I do that? This property. The limit of 3 times x is just the limit, or 3 times the limit of x, plus the limit of 2. I'm not going to do anything to that one. Now, it seems like I'm making this really complicated, but I was trying to break it down step by step. We're going to do this a much quicker way in a minute. But now these are the basic functions. As x approaches 3, this limit is 3. So this is 3 times this whole thing is approaching 3 plus this whole thing is approaching 2. The limit of a constant is the constant. This is 3 times 3 plus 2, which is 9 plus 2, which is 11. So I kind of broke it up. The limit of 3x and the limit of 2. I can bring, instead of 3x, bring the 3 out front, which is the limit of x, and that's how I did it. All right. After a couple tries, trying this a couple times, I think it'll make sense. So here, we have a polynomial function. I can split it up. This is the limit as x approaches 1 of minus x squared plus the limit as x approaches 1 of 1. All right, I can think of this as a minus 1, and I can bring it out front. Minus 1 times the limit x approaches 1 of x squared plus, this is just 1. All right. Okay, now, as x approaches 1, x squared approaches 1 squared. So this is negative 1 times 1 squared plus 1, which is just negative 1 plus 1, which is 0. Now, the shortcut's going to be this. Really, all I'm doing is putting 1 in and evaluating this. Negative 1 squared is negative 1 plus 1 is 0. So as I'm breaking this down and doing the limit of each piece, it's the same thing as if I just put the number into here. All right, let's take a look at another one and hopefully we'll see that. All right, this has 3 terms. So this is the limit. I'm going to break it up. Limit as x approaches 1 of 3x cubed minus the limit as x approaches 1 of 2x squared plus the limit as x approaches 1 of 4. All right, I'm going to move the constants out front. 3 times the limit as x approaches 1 of x cubed minus 2. A lot of writing. X approaches 1 of x squared plus the limit of x approaches 1 of 4. Now these are the basic functions I talked about in the beginning. These are powers of x, and that's a constant. So the limit of x to the third as x approaches to 1 is 1 to the third. So this is going to be 3 times 1. As x approaches 1 of x squared is 1 squared, which is 1. So this is minus 2 times 1. And the limit of a constant is a constant. That's just 4. So I get 3 minus 2 plus 4, which is 5. Now look, that's the same thing as if I just stuck 1 into here. So if it's a polynomial function, we're going to see in a moment, we can just evaluate it. The limits of a polynomial function are really easy. Just evaluate it. It's always approaching the actual value of the function. That's the case for polynomials. So not true for everything, certainly, but certainly true for polynomials. And I would get 3 minus 2 plus 4, which is 5, the same thing I got before. All right, so that brings me to this property we see in the book. It says if p is a polynomial function and c is a real number, then the limit as x approaches c of the polynomial is just the polynomial evaluated as c. So these limits are really nice. We just substitute the point we're taking the limit towards into the polynomial, and we're done. It turns out for rational functions, as long as you're not going to taking the limit towards a place where the denominator is 0, work the same way. All right, so let's try a rational function. So at first, I'm going to be breaking this down. Like I said, we won't be doing it that way all the time. So if it's a quotient, I could break this down into the limit x approaches negative 3 of 2, the numerator, over the limit as x approaches negative 3 of the denominator. Why can I do that? Well, this quotient rule. If I'm dividing functions, the limit is what you get when you divide their limits, as long as the denominator is not going to 0. As x approaches negative 3, the denominator is not going to 0. So we're fine. Limit of x approaches negative 3 of 2 is 2. And remember, I can just, this is a polynomial function down here, I can just evaluate it. Negative 3 plus 2 is negative 1, which is negative 2. All right, that would have been the same thing if I just evaluated it. 2 over negative 1 plus 2 is 2 over 1, which is 2. Well, where did I make a mistake? Oh, it's approaching negative 3, that's why. And that would be negative 1 and negative 2. All right, we're getting closer to the end here. So I'm going to evaluate this. This would be equal to the limit as x approaches 3 of the numerator divided by the limit as x approaches 3 of the denominator. Okay, as x approaches 3, this approaches 2 times 3, which is 6, minus 3 is 3. Limit x approaches 3 of x plus 5 is 8, so I get 3/8. I'll leave it like that. Alright, this is absolutely the last slide, so I'm not going to break it down anymore, okay, using the properties of limits. I'm just going to use the fact that if it's a polynomial function, the limit is equal to the actual value of the polynomial. So this would just be 2 times 3 plus 5, which is 11. Very easy, we just got to evaluate it. So, same thing down here. Let me do this one. This is a polynomial function, okay? So, as x approaches 0, this polynomial approaches what the polynomial equals at 0. 0 squared times minus 5 times 0 plus 3, which is 3. It's a rational function. As long as the denominator is not approaching 0, this rational function approaches what it's actually equal to at 5. So 5 minus 3 over 5 plus 5 is 2/10. That's the limit of that. Okay, so we've learned very basic functions, a constant, x, and a power of x. That led us to being able to evaluate polynomials and rational functions. And the bottom line is we simply have to evaluate them. So these are very easy limits to compute. All right, here's a journal assignment. You can apply that to all of these. Since, especially these rational ones, the denominator is not going to 0, you can simply substitute the value into the function. Okay, so make use of that property I talked about, that to evaluate a polynomial or rational function limit, just substitute the value into the function. All right, we'll talk to you later.